All right, so the whole year I told you I was going to show you how to tell if two means are the same. And this is called the equivalence test, and it's also called specifically the TOST equivalence test, and I'll explain that in a moment. Now let's just review on the problem of a traditional t-test p-value. Okay, so we run a t-test, we get a p-value that's less than 0.05, no problem. We reject the null and we move on. The problem exists when our p is greater than 0.05 and we are literally forced to say we know nothing. Now I want you to think about that. How useless is a science that can't say two means are the same? It's pretty useless, frankly. There are times when scientists are going to have to be able to say two means are identical or nearly identical. And this is where the TOST test comes in. After we find a non-significant p-value in a regular t-test, we run the TOST test. And if we find a significant p-value on our TOST test, then we can say that the two means that we're interested in are identical. If our TOST test also has a p-value greater than 0.05, what we can say is that we really don't know anything, but we can infer that, there's quite a bit of error in our study. We either need more participants, right, because we don't have enough power. We need better methods, better instructions, maybe stronger manipulations, all the stuff we talked about at the beginning of the semester. But ultimately, let's dive into this TOST test, okay? Now, in order to run the TOST, we have to figure out the effect size that we associate with not being important. And, what comes to mind is that 0.2 is small. So anything less than small would be my interval, would be, anything less than small between 0.119 of a Cohen's d and negative 0.119 of a Cohen's d would, in a perfect world, indicate that there was no difference between your two means, that your two means were the same. Now, there's a snag here because this is how I would like you to do it, but the snag is going to really shock you. So the snag is right here. The number of observations per cell to have an 80% power to detect equivalence. That means to be able to detect equivalence 80% of the time, if it actually existed, would be 329 per condition. In a within subject study design, you need 329 participants. In a between subject study design, you need about almost 660 participants to find equivalence. That's clearly not going to work, right? And so we go to it's just not. You would run a test that would never find equivalence. So what we're going to do is we're going to ramp it up to the medium level, okay? And the medium level of a Cohen's d, right, medium's 0.5, so just less than medium, is negative 0.499 and positive 0.499. And when you do the power analysis here, to be able to find equivalence, if it exists 80% of the time, you would only need to run 53 per cell or 106 per study. So it means like today's homework's going to have a lot of numbers in it, but ultimately it's a lot better than when we assume our Cohen's d of 0.2 is the cutoff value. So it is best for us as scientists to assume that this negative 0.499 and this positive 0.499, anything that falls in there that's less than medium is small and is not worth pursuing. Okay? Now, eventually we're going to develop better tests of equivalence, but this one works right now. It's actually a really good test. So it's less than ideal because honestly, if it were just theoretical or conceptual, I would say, why don't we just set our Cohen's d to 0.2 and negative 0.2 and roll from there? But the problem is that will never show equivalence. It never will, unless you have a massive sample size. So the best answer that currently exists right now for your studies is to choose a Cohen's d of 0.499 and a Cohen's d of negative 0.499. And I'm going to tell you right now that the TOST procedure, the hardest part is deciding what these limits are. And this is something that's up to the researcher. I'm making my decision for us as a class right now just based on a couple things. I understand that I would love to use the small value for Cohen's d. It just won't work. However, I also realize that if I find a medium effect, I'm not that interested in it either, right? Like, so really, really what I'm trying to say here is that anything that's less than medium, right, is not important. And that is my edge of my criteria. If something's just medium, if it has that Cohen's d of 0.5, I'm like, okay, it's worth pursuing. But if it's less than 0.499, it's not. And so this might be confusing to you, but this is just something you have to do. You have to figure out what your TOST interval is. And I did mine based on the Cohen's d's conceptual values. There are other ways to do it. I can send you papers if you ever want to do this test for a project outside of research methods. But I'm letting you know that there is a procedure to test for equivalence. And let's talk about that on the next slide. So here we have our TOST approach. What's it stand for? Two one-sided t-tests. So all this means, like, one-sided is a one-tailed t-test. That's all they're saying. So there's two one-tailed t-tests. That's the name of it. Two one-sided tests means two one-tailed t-tests. No big deal. Okay? I'm moving on to the next bullet point. Now, there are three null hypotheses that we're interested in. And I think you'll start to see why you would need so many observations to find equivalence. Let's start with the null hypothesis we know. That one's at the top. That's the null hypothesis for any two-group comparison, whether it's an independent samples t, a dependent samples t-test. One of the follow-up tests that we've been learning are also t-tests. So a lot of things are t-tests. They also have this null, a t-shaped distribution. Right? It tells you the probability of sampling any mean difference from negative infinity to positive infinity if the null were true and the true mean difference were 0. That's why it's centered around 0. Now, all we can use this distribution for is to disprove the null. We can't prove it correct. So we're trying to figure out additional tests when we do not find a significant difference that we can do that allows us to say two means are equivalent. And this is the TOST procedure. So in the picture underneath here, underneath that specific random sampling distribution of mean differences if the null were true, we can see H0 and H1. Well, H0 would be our null hypothesis. And our null hypothesis for both TOST tests is essentially that our observed mean difference is larger than the mean difference that is predicted from our cutoff Cohen's d. So let me just restate that, Cohen's d equals mean difference over standard deviation. Cohen's d times standard deviation equals mean difference. So we can convert any Cohen's d to a mean difference. We can conversely convert any mean difference to a Cohen's d by just calculating Cohen's d. So what we notice here is we have these two areas of the null hypothesis. So we're saying if any of our mean differences are greater in absolute value than 0.499, then we are not going to assume that the two means are equivalent. The same thing, like it works on both sides. So you can see there, if our mean difference is greater in absolute value than 0.499, we're retaining the null hypothesis. Okay? So that's the general idea. If our mean difference falls in the H1 area, we're going to say that we've disproven this null hypothesis, that our two means are different, and we have disproven that idea, and so the two means are the same. So all I'm saying there is if our mean difference falls in that white region, what we're going to do is say those two means are the same. Now, how do we actually do this? We actually have to do two one sample t-tests. Now, the first test is focusing on the right side of the distribution. So it's saying, is your mean difference significantly smaller than the mean difference predicted when Cohen's d equals 0.499? So that is our null hypothesis. You can see that this distribution is centered around 0.499. Right? You can see that there's two null hypothesis distributions down there. Only look at the one on the right. That's the little curve. You can see that the 0 point of that distribution is lined up with our upper limit, change y, right? That's the upper limit. And that most common score is 0.499 is shown on the graph, right? Well, what we do is we test our mean difference, right, whatever that is, against the mean difference that we find when we convert that Cohen's d of 0.499 into mean differences. Or to phrase it a different way, we're testing if our sampled Cohen's d is significantly less than the Cohen's d of 0.499. It's the same thing. It means the same thing because mean differences and Cohen's d's are interchangeable. So it's really not that weird to say that. So our first test just tells us if our sampled Cohen's d is significantly less than the cutoff Cohen's d of positive 0.499. That's the first one, right? And if that's true, we're halfway there. If our mean difference is significantly less than the mean difference of 0.499 has stated like in our null prediction, and that was stated because that's the place that's less than medium, right? If it's significantly less, if our Cohen's d is significantly less than 0.499, then we don't know if they're equivalent yet, but we're halfway there. The other test we have to see is also if our sampled mean difference or our sampled Cohen's d is greater than negative 0.499, if it's both of those conditions, if our sampled mean difference or our sampled Cohen's d, same thing, they're convertible to each other, right? If that is both significantly less than 0.499 and significantly greater than negative 0.499, we say we have equivalence because we don't have an effect that's at least a medium effect size. Okay? And that's basically how it works. You run one t-test, seeing if your mean difference is significantly different than the mean difference predicted from a Cohen's d of 0.499. And we do another t-test to see if our mean difference is significantly different than the mean difference predicted from a Cohen's d of negative 0.499. That is it. If both of these tests are significant, then we say that our TOST test is also significant. And if our TOST test is significant, then we're able to say our two means are the same. And that's how the test works. All right, so we know when to use the TOST procedure. We know kind of how it works, but we need to see some output to really understand. So this is the output you're going to see on my program. It's saying your comparison, you compared two groups, a control group and an empathy group. Your TOST your upper limit t-test was negative 5.37, degrees of freedom 210, p-value is essentially 0. TOST of the lower limit, the t-value is 1.9, the degrees of freedom is 210, and the p-value is 0.03. The original t-test is presented on there and it's non-significant. You can see that. And you can see the solution, right? The take-home. This test shows equivalence. This mean difference is 0, essentially. So these two means are the same. And so like you run your TOST procedure, then you write it up. The TOST procedure for testing equivalence among means, cite Lackins et al., 2018, it's from this paper right underneath, indicates that participants' pain treatment scores were equivalent across the experimental and control conditions. And then you report the t-value for the least significant test, okay? So in this case, I'm reporting the t-value for the lower limit. The lower limit. So you got my t, 210 equals 1.9. My p-value equals 0.03. And that's it. That's how you would write it up. This shows that our two means are the same. Now, when do you use this test? I would recommend that you use it as a follow-up to any non-significant mean difference calculation. And you're like, wait, what are these? We do have the one sample T and one sample Z. You can use them there. I haven't made them for you for there because we won't be using them there, but you can use them for there, right? You're going to use it for an independent samples t-test or a dependent samples t-test. You're going to use it for any like non-significant main effect follow-ups with only 2 levels. So you can think about it this way. You found a non-significant main effect in a factorial ANOVA study. So you have this non-significant main effect. Let's say that main effect only had 2 conditions, okay? So you can have that, right? Not all main effects have more than 2 conditions. You can have a 2x2 factorial design. And so if you have a main effect from a factorial ANOVA with 2 conditions, you can run and you find a non-significant difference there in the ANOVA, non-significant main effect, you can run the TOST on those 2 means. You can also run it on any non-significant follow-up t-test to a one-way ANOVA. That's 3 or more groups, right? That's relatively, yeah, you can do it there. You can run it on any non-significant follow-up t-test in a factorial ANOVA. So in the one-way ANOVA, you know how we did a bunch of follow-up t's if we found significance? Well, you can do it when you find non-significance too, but you can run a TOST afterwards, right? You don't necessarily have to run the t-test. Now, if you're in like I just said, in a factorial ANOVA, and you have a non-significant follow-up test, you can run the TOST on that as well, okay? So that's just like, oh, your main effect has more than 2 levels. It has 3, 4, or 5. You can run a TOST on any of those mean comparisons that ended up being non-significant, right? The TOST is a follow-up to a non-significant 2-group comparison. And then, in terms of the interactions, where we are taught to do follow-up t-tests to examine interactions, right? I know we're taught this in the department. What we can do is when we find a non-significant follow-up to an interaction, we can take the 2 means that we used in that follow-up and examine them with a TOST procedure as well. Now, let me just reiterate the interaction stuff because it's new, it's fresh, it's right here. So when you have an interaction in a factorial ANOVA, you can break your data 2 ways. You can break it, like for this data over here, you can break it by alone versus team. So let's say I'm going to do that. So then I break it by alone versus team, and I run a t-test on the blue and orange bars in alone, which represent monitored and unmonitored. So that's one t-test I'd run. And that t-test is going to work out non-significant. You can see that. Those 2 bars are the same height. And so then what I could do is I could run a follow-up to this non-significant t-test, a follow-up TOST to it to see, okay, do these mean differences fall in the range of not importance, right? Do they fall in that range from medium to medium? If they do, I can say the 2 means are equivalent. Now, additionally, I would look at the t-test for team blue versus orange, and that's going to be significant, so I would not run a TOST test on it. Now, that's just one way to break up the interaction. The other way I can break it up is I can break it up based on monitored and unmonitored. So I'd break it up, blue bars and orange bars get paired together. So if I'm looking at monitored, right, I see that monitored alone and monitored in a team, they have the same score. That would be a non-significant p-value on a t-test. And so then I run the TOST afterwards to see if those 2 means are equivalent. I wouldn't do it on the 2 orange bars because those are going to show up significantly different. Again, if they didn't show up significantly different, I would run the TOST on them as well. And so I do think it's important to run a TOST when you have a non-significant 2-group comparison. The worst case, it's going to take you 5 minutes of your life, and you're going to not know, you're going to still know nothing. Best case scenario, you're going to be able to say that your two means are statistically the same using the TOST procedure of Daniel Lakens, actually. So essentially, that's the concept behind what we're doing. Now let's actually go run a TOST procedure. All right, everyone, how do we run the equivalence test or the TOST? So we look for equivalence test. I'll put TOST down there. I'll probably change that up later, but not right now. And you have to say, okay, I have a t-test that's non-significant. I want to examine that to see if my two means are the same. So that's the whole situation. So what you have to do is you have to enter in your data. Now this data currently is entered as if we had a dependent samples design or a within subjects design. You notice that they're the same thing, right? So it's just in a within subjects design, right? Or a dependent samples design or a correlated samples design, whether that's coming from a t-test, whether it's coming from dependent samples t-test, or it's coming from a follow-up to a within groups component in the ANOVA. All you have to do is enter in your data from your two groups. Now, let's just say this data came from a design that was correlated samples design, correlated samples, dependent samples, within subjects design. Okay, what do? We enter in our data. We got to make sure that we have an equal number of observations in our data. No problem there. We're going to label our two conditions. Group 1's the empathy condition. Group 2's the control condition. This is just important for the output that's going to come in a second. Is dependent samples. So maybe it's a poorly worded variable name, but that variable is dependent samples. You put a Y down if it's a dependent samples t-test or a dependent samples follow-up or a follow-up to a component that is a within subjects component in ANOVA, either a one-way ANOVA or a factorial ANOVA. And it's just the same thing. Were there the same participants in both of these conditions? If they were, if this 3 and 4 come from the same person and this 5 and 5 come from the same person, is this dependent samples equals yes? So then it says you're done, hit run and get your results. Okay, boom, we hit run, we get our results, and what we have here is the comparison that's being made in case, like just in case we get lost, right? It's really important for us not to get lost. And then we get our TOST. This is just saying, well, what is it? It's TOST the upper limit, TOST the lower limit, and the original t-test at the bottom, just for the sake of understanding. And what I'm noticing here is that my original t-test had a p less than 0.05, so we would never do this. So let me just change that around, see if that's going to work out a little bit better. All right. I'm going to run it again. I just changed the data just so it makes sense, right? There we go, right? So here's a situation where original t-test showed that our p was greater than 0.05. And then our TOST on the upper level, it's looking promising. Our p is less than 0.05, but the lower limit, we are not greater than the lower limit. Our p's 0.6. So we still know nothing. That's how we would interpret this result right here. We know nothing. And honestly, I would expect that in this kind of result. You know what the problem is here? We don't have enough participants to push this p into the 0.05 range. So really, when I see this, I'm kind of like, you know what's really going on here? If I run a better study, I probably have a significant difference, right? Until I do that, I have neither a significant difference nor do I have equivalence, because likely equivalence doesn't exist in this research question outside of my poorly collected data. Okay? All right, so that's basically what we have here. Our p-values, our degrees of freedom, our t's for all these different tests, and our conclusion. So I want to say, okay, let's make this a between subjects condition. And all I'm doing is just putting in more data here. I'm going to say like, oh, this was my original data. And all I'm going to do then is just add another one of these and add another one of these, but I don't want them to be equal in size. So now I have like more observations. Empathy and control are still the same. This I'm just going to change to no. And then I'm going to click run. And we're going to see what happens. Okay. So we have a situation where we're close again. We still know nothing. So first thing, our control versus empathy, our TOST upper test is significant, but our bottom test is not. So, and then we see our original t-test was not significant at all. Now you can tell we're kind of close to making the conclusion that these two means are equivalent. So let me just go ahead and add a couple more data points to this data set and see if that pushes us over the edge. Because I want you to see, you're never supposed to make up data. This is just for the sake of understanding stats, right? You put real data in here or data I give you in problems. But I'm going to click run, and I hope we get to see what happens when we're still there, but we're not close enough. What I'm gonna go ahead and do then is I'm just gonna double my sample size. I'm gonna say, okay, I reran my study and I'm doubling my sample size for both conditions, right? And I'm gonna go ahead and copy these and paste them in there. And realize you would never do this. You just put the data I gave you in there. But I'm really just trying to show you what happens when our two means are equivalent. There we go. This test shows equivalence. This mean difference is 0, right? This is what you're going to see under that circumstance. And I have quite a lot of observations in here to make that happen. And you can go back to my lecture to see that you're going to need a lot of observations to make a conclusion about equivalence. Now, what I'm going to do is I'm gonna make your life easy, and I'm gonna go ahead and I'm gonna post an Excel file with, it's only gonna have 2 cells in it, group A and group B. I'm gonna tell you to run it. I'm gonna tell you to run the equivalence test on that specific problem just to make that happen. But essentially, that's it. That's how we run it. It's not that hard. And this allows us to say our two means are equivalent with the caveats that I talked about in the lecture. Like in an ideal world, we'd run 1 billion participants. We'd be able to say that the effect is less than small, right? But here we're going to have to like settle for less than medium, okay? But essentially that's it. That's how it works. All right, so here's your homework. It's an Excel file just to make it easier for you to get the data into the program. So when I copied and pasted it by just selecting all of this and copying it, it allowed me to paste it right into the program. So that's nice to know. And then I want you to run 3 tests. Number 1, run a TOST for dependent samples, same number of n. Run a TOST for independent samples, same number of n. And I might as well fix that typo while I'm here. And then I want you to delete 5 total observations of your choosing and run the TOST for ... the appropriate test after you remove the 5 data points. Hint, after you remove 5 data points, your design is no longer balanced. And by that, I mean you don't have the same number of observations in each condition. So there's only one of the TOSTs you can run, but I'm not going to tell you because that's part of the assignment. All right, but that's your homework.